So thank you all very much for having me here. You might ask yourself why a particle physicist is at this type of conference. And the one thing we have in common, like Amut kindly explained, is data.
Just gone to sleep. It needs to be woken up.
Had to. There you go. Perfect. And the scales of data we're talking about is big data. So Hannes talked this morning about how a petabyte of data is usually something people like to consider big. So let's talk about 40 million petabytes of data. So here you can see typical data sizes for Amazon cloud storage, what's uploaded to Instagram, versus how much data is produced at the LHC, roughly 40,000 exabytes every single year. So this is a completely different scale than anything we're dealing with in industry. And this is the amount of data that's produced. And the amount of data we can afford to keep is only a fraction of that. And I'll explain further in the following why we can only afford to keep so little. So we've had to deal with massive data for a very long time. With the rise of the internet, the community now, the world needs to deal with big data. We've had to deal with big data since the 50s. And actually, the first computing cluster in the world was located at CERN. So this was our very first computer, the Ferranti Mercury. It was not a transistor-based computer. It was a vacuum tube computer. It had magnetic core storage. You see the 4 boxes in the back there, 32K by 20 bits. So we couldn't even fit a single LHC collision on all of these storage tapes. We didn't even have Fortran. Luckily, our next computer did. Our next computer was in 1963, IBM 7090, transistor technology with Fortran. And what we actually used this computer to, which fills the whole room, was to analyze these type of frames of particle data. So we had these spark chambers. Charged particle goes through high voltage, and it creates a spark. And we would digitize those pictures and analyze them. And we could analyze 300,000 frames of this spark chamber data. So it was a huge success. And there will be a talk tomorrow about I/O, I think from Andrew. And one of the first things we noticed was that we overinvested in compute. So the CPU of this computer was blocked during I/O. So we immediately realized that the bottleneck for us was actually I/O and not compute. 1972, I just wanted to show you this because I think it's beautiful. We got the most powerful computing system in Europe, CDC 7600. This is it arriving at the airport in Geneva on a Pan Am flight. And you can see here the loads of one, basically, computer. Where are we today? Today we have 2 CERN data centers on site in Geneva with 450,000 processor cores, 10,000 servers. Although 90% of that compute is through private cloud based on OpenStack. This handles 45 petabytes per week, and the total storage capacity is 3 exabytes between tape and increasingly disk. And the reading rate from the system we're very proud of, we're serving all of the experiments at the LHC, is 1 terabyte per second. So we also do compute, not just physics. We also needed to share all of that information, so the World Wide Web was invented at CERN in 1989 because we have collaborators all over the world and we needed to share that information swiftly. We released that in the public domain in 1993 under an open license later on, and I found this really nice quote from the WW8 conference in 1999, where a person who was sipping Chardonnay at the evening reception, courtesy of Bill Gates, said Microsoft will have bought the World Wide Web by next year. So luckily, that didn't happen. We've even invented our own binary data format. So we talked a little bit at the event yesterday about, okay, are you using kind of databases anywhere? No, not really. We use SQL and Oracle for maybe some very tiny things where we have very, very small amounts of data. But we actually have what's called a root T-tree. It's a columnar data format that we developed almost 30 years ago, and we store 2 exabytes of LHC data using that format. And we'll have a new format for the future that will be used to store tens of exabytes of data. And we have a full data analysis stack built on top of this data format. So everything is basically in-house. Okay, so where is all this big data coming from? This is my workplace. This is 100 meters underground. There's this Geneva lake here, city of Geneva. I work at this experiment called CMS. It's a 30-kilometer long ring. And what we do there, it's a vacuum tube, basically, a 30-kilometer long vacuum tube. Everything is on minus 270 degrees Celsius. We accelerate bunches of protons to almost the speed of light using electromagnetic fields. So we have bunches of trillions of protons spaced by 25 nanoseconds. We accelerate them in opposite directions. So one goes around this way, the other one goes around this way. And when we've filled the whole ring with protons, we have 2,500 bunches of these protons circulating at 11,000 times per second. And we keep them on track, because they would go straight ahead, using very powerful magnets. So what we do next is that once we get close to one of the detectors, you see here we have CMS, LHCb, Atlas, Elise, 4 detectors. Every single time we're underneath, inside one of these detectors, we use powerful magnets to squeeze the bunches of protons tighter together, so they're denser. We bend the beams so that they can smash into each other. And out of the trillion protons and trillion protons, roughly 60 pairs will interact every time the bunches cross, because most of it is air. The probability that they will hit each other is extremely small, so we need a trillion of them. Every time that happens, the energy of the incoming protons is converted to the mass of new outgoing particles that shower through the detector. Not one particle, not 2 particles, but thousands of particles. We smash them together. That's the energy of the incoming protons. That m, the mass of new outgoing particles, is one of the particles we know of the Standard Model. These are all of the particles we know. All of us are built up by these U and D quarks and electrons, basically. So we try to produce all of these different types of particles and then measure them in the detector. Your camera measures only photons. That's this gamma here. So it only needs to be sensitive to one type of particle. We need to be sensitive to all of these particles, and they're very different. The masses of these particles span 9 orders of magnitude. So we need detectors that can detect all of them. And this is an example of such a camera. In the middle, the protons hit each other. And they produce new particles that shower through the detector, which is layered like an onion. So you have the inner charge particle tracker. You have a huge magnet, 4 Tesla magnet, that has the job of bending the particles so we can measure their momentum. And then we have muon chambers on the outside. The muon is a particle that doesn't really interact with matter very much, so it can shower through the whole thing. So you can see an example. Let's say we want to see this muon. What we see is that the muon is measured in this inner part of the detector. It's a charged particle. It's bent by this superconducting solenoid, this magnet, so it curves. And from the radius of this curvature, we can measure its momentum. We also need to measure these quarks, and we measure them by seeing their charged particle track, and they dump all of their energy in the hadron calorimeter. So these are the particles that are visible to us. Some of you might have heard about the Higgs boson. That's an example of a particle that's invisible to us because it has such a short lifetime. So the Higgs boson is another particle we want to see, but we never really see it. So the lifetime of the Higgs boson is 10 to the minus 22 seconds. It's produced and it instantly decays. For instance, it decays instantly into 2 Z bosons that also then instantly decays into 2 leptons. I know it's a lot of jargon, but one particle decays to 2 that decays to 2. So in the end, we see these 4 particles coming out of the collision point. We sum up all of their masses, and that should equal the mass of the Higgs boson. So when we announced the discovery of the Higgs boson, we had to collide trillions of proton pairs. Collision, 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 collision. And 10 of these collisions, that's that red peak that's growing, more and more data comes in. This red peak, you produce more and more and more. 10 of those collisions was what constituted the Higgs discovery. So that red histogram is 10 collision events that were comparable with the existence of the Higgs. So it's so improbable to produce some of these rare processes, and the only way we kind of see them is indirectly. Okay, so what's the deal with data? Well, for every collision, we have now a megabyte of data. In the future, it will be almost 10. We have 1 billion of collisions per second, so we roughly have a petabyte of data generated every single second. And I remind you, we are 100 meters underground in a radiation-shielded cavern. Luckily for us, we don't need to store all of that data. If we look at the probability of producing anything in our detector, the probability of producing a Higgs at 13 TeV, which is the energy the LHC is operating at, is 1 in 1 billion. So saving all of the collisions is not useful, even if we could. So we can afford to discard some. Okay, so we are back here. A collision happens, a petabyte of data per second, collisions every 25 nanoseconds. Here's where our data system comes in. This is the CMS detector. Collisions, again, happen in the very center here where you see this beam pipe. The beam of protons is 2 millimeters wide, roughly. Okay, a collision happens. The full information of the event is temporarily stored on ASIC inside the detector, and it has some buffering limit. That buffering limit is 10 microseconds. So that's basically the size of the buffer. Now we have buffering limit time to very swiftly analyze that data. So we developed our own low-power gigabit transceivers, which are radiation-hard ASICs, to send 10 gigabits per second out of this detector. We have 50,000 of them. We send 44 terabits per second via high-speed optical links to what we call the level 1. This is a subset of the collision information. It's 200 kilobytes. The full event information is orders of megabytes. This subset still corresponds to 5% of total internet traffic, again, in a radiation-shielded cavern 100 meters underground. That data is received by an FPGA farm. Here we have 1,000 high-end Xilinx, aka now AMD, FPGAs. These FPGAs have 10 microseconds to fully reconstruct the event and then do a filtering that discards 98% of all of the collisions. So out of all of the collisions we take, we discard 98% of them within 10 microseconds. So what does this system do? It's roughly 20,000 euros per FPGA. We have 1,000 of them, and I have one binary output. It's level 1 accept or level 1 reject. If there's a level 1 reject, we send a 0 back to those ASICs. They also can receive information from the FPGA. If it's a 0, we say, flush the buffer. We're not interested in this collision event. We will never see that data again. No human will ever interact with that data. If it's a 1, if and only if, do we send a signal back to the detector and we say, hey, read out all of the event information. This level 1 trigger just saw the 200 kilobytes. It didn't see everything. It can only do a very coarse guesstimate of if this collision was interesting or not. Now we want all of the data. Now, why am I not reading out for every single collision all of the data? That's because every single event is 4.6 megabytes per second, basically. So the data we can afford to read out of the detector is 1 megahertz. We take collisions at 40 megahertz. We can only read out 1 megahertz. And even that rate corresponds to 4.6 terabytes per second. The problem for us is that if we would read out this number for the full rate, you have to multiply this number by 40. If you multiply this number by 40, inside this detector, you need to put so many services, ASICs, powering, cables, to read out the data. That means your detector is not sensitive to anything anymore, because you filled it with cabling, basically. So even if we had money to read out all the data, it would completely destroy our detectors because it's so full of cables, basically. So we cannot. So this is what we can afford to read out, these 1,000 DVDs per second. And now it's our job to send that out of the detector. So we now have 98.125% of the events rejected. We're sending out data at almost 1 megahertz. Collisions were 40 megahertz, now we have 1 megahertz, roughly 750 kilohertz. This is sent with 100 gigabits per second data links, almost 600 of them, on 200-meter-long fibers from the detector to the surface. This is then received by 40 32 by 100 gigabits per second switches that sends this data to the high-level trigger. We still have too much data to read out and store. So here we have a second filtering system consisting of 30,000 CPUs and GPUs that now need to reject a further 99% of all of that data because it's still too much to read out and store. And here, very recently, we switched to a heterogeneous computing farm to speed up the amount of compute we could do. So out of all of those CPUs, we attached a GPU to every single node because we realized that there were some of the compute were faster on a GPU, so we did some processing on CPU, offloaded things to the GPU, and sent it back to the CPU. And by doing that, we can increase our throughput by a factor of 2. And reducing the power consumption. So here we have a heterogeneous farm. Okay, after this, we've now rejected 99.98125% of the events. We're sending data at roughly 7.5 kilohertz, 35 gigabits per second. And we send it for full offline reconstruction and storage. That's 0.02% of the collision events that's remaining. That's very little. And what happens to all that data once we decide to keep it? What happens to that 0.02% of the events? It's sent to the worldwide LHC computing grid, which consists of 170 sites in 42 countries, 1.4 million computer cores, 3 exabytes of data storage, global transfer rates of 260 gigabits per second. Okay, we do all of this because we want to measure the parameters of the standard model of particle physics extremely precisely to the 5 sigma, 5 standard deviation point, which means we need high statistical significance. So to make sure we select the right 0.02% of data, our algorithms needs to be extremely fast to get more data through the system and accurate to select the right type of data. We already discovered the Higgs boson. What are we looking for now? Well, we know there needs to be physics beyond the standard model of particle physics. We can't explain dark matter. We can't incorporate gravity in our theory. So there needs to be new physics. And that's only produced 1 in a trillion. So we need more data. So in 2031, we will upgrade to the high-luminosity LHC. Whereas before, on average, 60 pairs of protons would interact, in high-luminosity LHC, we'll have 200 simultaneous interactions. And we need to detangle and reconstruct every single one of these green lines, which will require way more compute. The data complexity is massive. The future CPU and storage needs versus budget is also going to be very dramatic for us. If you look at the CPU needs, disk need, tape need, we're going to need as a function of the year. Around 2031, here you can see in the blue line what we're going to need, and in the band what we can afford. So what we've had to do is redesign all of our algorithms to be more efficient and to reduce the amount of data in a clever way. So our challenges to do good physics is the following. We need to get the data out of the detector while minimizing the dead material, because then our detector is not good anymore. We need to process all of that data. Reconstructing it takes 20 seconds per event. And we need to store all that data. So data is our main precision bottleneck at the LHC. So in order to deal with this high complexity data, what we have discovered is that machine learning can be one of the ways in which we can achieve all of those goals. Machine learning can be a very efficient function approximator, so we can do things highly parallel on the same kind of latency budget with higher accuracy. So what I'm working on is fast machine learning inference on specialized hardware. We work inside the detector on ASIC, where you have to do inference within a few nanoseconds. On FPGAs in this level 1 trigger farm, where you also have maximum 1 microseconds of latency per algorithm, and on the GPU system on the surface. Now, the revolution of machine learning, AI, is now seeing this trend of extraordinarily large neural networks trained on very large data sets. Large data sets we have. So these extraordinarily large neural networks, this trend is something that doesn't really seem like it's going to end. If we look at the performance, how the loss changes as a function of how much data you throw at the problem, how much compute you throw at the problem, you see the performance basically improving very smoothly. So here you can see this, the loss going down as a function of compute, dataset size, and size of the model. And we see no ending to this scaling, which means our models will continue to get bigger, bigger, and bigger. We also see that while these models scale at a factor of 240 every 2 years, actual hardware only scales by a factor of 2. So here you can see floating point 32 compute versus specialized compute for machine learning inference versus the scaling of these type of models. So in the words of system people, we're starting to have a little bit of a problem with big machine learning models. So there was a really nice talk by Lidong Zhu, VP at Microsoft, that said, you can't scale by throwing hardware at the problem forever. Scale exacerbates hidden flaws and inefficiencies, everything fails, sublinear. So in his talk, he was saying, hey, the way you are designing these LLMs, these huge models, it needs to fundamentally change now. So why am I talking about all of this in this talk? Well, he brought up a few examples on what you should do for LLMs in the future. One was stop using floating point, but use integers. So for instance, here to the left, you can see the power you save if you move from floating point to integer. Here you can see the size of the chip in floating point versus integer. And a lot of you have probably heard about this paper about the ternary LLMs. You can get great performance with ternary LLMs. So to solve computing's energy problem, use integers. Okay, great. Secondly, it can be very expensive to do runtime computations. Instead, use lookup tables for every single input you give an output. It can be way more power efficient. And lookup tables are basically among the simplest, only the simple can scale. And we have actually been doing these things for years. Everything is done in integers. Everything that can be computed as a lookup table is a lookup table on the FPGAs or on the ASICs. So for us, this is great because now everyone is interested in efficient machine learning, and we have, out of necessity, been designing novel techniques of doing this for a very long time. Why have we been doing that? Well, if you look at the latency requirements of our system versus the amount of data that goes through that system, Google Cloud is this green thing, Netflix is down here, we are this blue thing on the very, very left. So our challenges are completely at a different scale of what industry actually sees. The size is the amount of data we have to process every year. So this is just data in the terms of machine learning world. I don't know, are you familiar with the tiny MLPerf, stuff like this? Yeah, so like machine learning benchmarks for efficient edge compute, like headphones or smartphones. TinyML is down here. Our benchmark, this is this transceiver protocol, 10 gigabits per second. Our inference requirements are all the way up there, that blue thing. So we've been forced to really design brand new techniques to handle this data. So inference on ASICs and FPGAs has been a necessity for us. And now basically everyone else is also needing this to handle massive throughputs. Okay. So what does such a system look like, an FPGA system? Here you again see the slice of the detector. We have 1,000 FPGAs, And they are split in the following way. We have 400 of them that only processes this yellow subdetector, 200 processing this little green one with huge data input, 6.4 terabits per second to the system, 100 doing FPGAs. Then we have 60 that merges all of the information, and some in the end that does the final yes or no. And the whole latency of the system is 12 microseconds, but for every single block, it's on a tight clock. So at 5 microseconds, all of this needs to be done. And to give you a bit more of a feeling what the system looks like, here you can see Noah walking through the racks, basically, of this level 1 trigger farm. So you just have racks on each side in this place. So with the techniques that we've been developing, we actually expect to be doing 40 billion inferences per second using libraries we've been designing in-house, which is the same amount of inferences that's done at the whole of Google, I've been told. And these libraries is what has allowed us to do that. So first and foremost, why FPGAs? The reason we are using FPGAs is basically latency. If you don't have a latency problem, never touch an FPGA. There's no point. So we can use resource parallelism to work on different parts of the problem and different data simultaneously. Has a very high bandwidth via pipelining, and we need to process 5% of the total internet traffic. And it's latency deterministic. So we can have no slack of 1 nanosecond up or 1 nanosecond down. It has a repeatable and predictable latency. So here you can see an example to the right, how actually in the system with 162 FPGAs, we are simultaneously working on 18 collisions in the system all at once. And only after we've sent the data to the surface do we bunch all of that information into discrete collisions based on an ID number that we have. FPGAs is basically field programmable. It has a bunch of resources and interconnects. You can reprogram it as you like. Before, it was only used for prototyping ASICs, and now it's used a lot for high-performance compute. It has block RAM memory, roughly 2,000 units, logic cells for arbitrary small arithmetic and memory, flip-flops that registers the data in time with the clock, and the digital signal processors that specialized units for multiplication. And if you look at the neural network, usually all the multiplications of the neural net goes on the DSPs, addition on the logic cells, and the activation functions we always pre-compute and store as a lookup table. So obviously people have been using FPGAs for a very long time and been using them to do machine learning. Why do we need to make our own tools? Well, the way you usually program an FPGA is either by writing hardware description language or Verilog, which usually an engineer does, or you can go one level up in abstraction and program in high-level synthesis, so write C++ code with some directives that talks to the compiler, and you give it to a compiler that you get from your vendor, depending on where you bought your FPGA or if you want to print silicon. The problem for us was every time we tried to use a tool from industry to put machine learning on FPGAs, it was too slow. Nothing could reach 50 nanoseconds latency. So we realized very quickly, okay, we actually can't do machine learning in the system, or we need to reinvent something. So we attacked this part together with AMD's Xilinx on how to write efficient HLS to make nanosecond machine learning models a reality. So the way it works is the following. You start with some model, but you need to do some form of compression of that model first. You pass it to our library, HLS4ML, that will write that C++ code for you, basically, with the correct directives, emulate that code, everything in Python, and then run the synthesis and build the firmware, which can give you either a co-processing kernel, so you can plug an FPGA into your CPU and accelerate inference, FPGA custom design, as we have you integrate an IP into your whole FPGA cluster like we have, or print silicon, all these things possible with the same library. Here you can see an example of a small convolutional neural network to classify digits and how it maps onto an FPGA. Now, we have what's called a data flow architecture. It's fundamentally different from a Van Neumann machine. Everything is based on availability of data. As soon as data becomes available for the next process, it starts the next process. So it's super efficient. In contrast to a TPU or a DPU, we tailor the hardware for a specific model at design time. So decisions are design time. We build the firmware for your model. Why? because you can squeeze in as much as possible on that area, and it's more efficient than having some huge generic TPU. Each layer is a separate compute unit. You can do what you want, make the clock faster, quantize it how you want. And the biggest thing is that everything needs to stay on chip. We tried looking at using external memory, but the latency bottleneck with sending data to external memory and back killed us instantly because we have 50 nanoseconds latency. So even if we want to put big transformers onto our FPGA, in reality we cannot because we need to stay on chip. So one of the biggest challenges we had was really developing and using techniques to compress the models as efficiently as possible. And the biggest gain, which we already saw in Lidung's talk, is quantization. So when you train, everything is floating point 32, great, big dynamic range, very granular. What we want to do is use integers instead, so fixed point precision. So we want to round and clip all the numbers and put them in little buckets. So for a bit width of 4 and 0 integer bits, you have 60 numbers between -1 and 0.9, something like that. Why do we want to quantize and put our numbers in buckets? The reason is, if you look at the amount of operations you can do, you can go a factor of 200 higher in throughput by quantizing to binary, for instance. Also, the size of the models can grow by a factor of 30 if you go from floating point 32 to binary. So you can fit everything on chip. So this is something we needed to do. The problem is, if you train a model in floating point, and then you quantize it afterwards, it's lossy by definition, basically. So once you start reducing numerical precision, at some point it's a coin toss. So that didn't really work for us at all. So what we instead did together with Google was to design a library to do quantization-aware training. So every time you train a model on the forward pass, every single weight is rounded and clipped, basically. It's quantized. So the neural network will adapt the weights to what it will have on hardware. So it's kind of hardware-software co-design at training time. And we made this extremely easy. So if you're used to keras, this is Q-keras, where you add a Q in front of the layer you want, and a quantizer. So quantized bit 60 is bit width of 6, so you have 2 to the 6 buckets, and 0 integer bits, because usually the weights of a neural network can anyways be between like -1 and 1, so it's okay. And you can even, here you see I put quantized bits with a bit width of 6 everywhere. That doesn't need to be the case. What's super cool with FPGAs is that on a GPU, you need some int8 kernel if you want to quantize things. On an FPGA, you can use any numerical precision you want for any single operation. So every single weight of my neural network can have a different precision. That's called heterogeneous quantization, and that's the most powerful thing you can do to maximize accuracy and minimize size. So here you can see an example of a crazy model that we found to really have the same accuracy as a homogeneously quantized model. So here I'll guide you through it. There's a lot of numbers. This model has one layer with a bit width of 4, a ternary layer, one layer with binary weights, and a bit width of 8 for the bias terms. You can have these completely crazy models. And if you compare the energy consumption of a model that's been heterogeneously quantized versus homogeneously quantized to 6 bits, which is very little, you use basically a third of the energy, and the bit size is a fifth. So you can really save a lot by going this way. We also have an optimizer, a neural architecture search, where you can, because how do you decide on what quantization to use? You can scan over bit widths to find the Pareto frontier of the most accurate models at the smallest size. At the same time, you have to optimize the filters or nodes per layer, because that will obviously change once you quantize. You might need more neurons or less. We also support different types of quantization. So the Hessian is kind of is a description of the loss landscape of a model. So if you have a model like ResNet, you look at how much small perturbations of the weight affects the actual output. So a high Hessian trace means that the curvature of the loss is very high. So if you have a small change in the weight, it has a big effect on the output. If the Hessian trace is small change of the weight hardly affects the output. So you can also optimize the quantization looking at the Hessian. If I quantize this, what's the effect? In this case, quantize the 52nd layer a lot of ResNet, but the first block not at all, because the curvature is different. And all of this we've put together with AMD Research Lab in a common library called QONIX, where you can quantize using a bunch of different tools. You have an intermediate representation of quantized models that can talk to different types of backend compilers, our library or AMD's own backend library called FIN. Then finally, in this age of deep learning, you're database people, you're then used to tabular data, maybe. Not everything is pixels of an image. If you have tabular data, most likely decision trees are what you need. And even for very, very difficult problems with tabular data, tree-based models still outperform deep learning. This is the founder of scikit-learn, by the way, that wrote this paper. So decision trees are fantastic because you can get the same accuracy at a fraction of the latency and a fraction of the resource cost. And we also support the translations of those models into FPGA firmware. Okay, so now quickly, what do we use these things for? A few examples. So let's go inside the CMS detector. Inside the CMS detector, we have extremely granular detector cells, like this one here, the HGCal. It's inside the detector, it's in high radiation, so it's cooled to minus 30 degrees. Every ASIC processing inside the detector needs to be low power, sub 100 milliwatts. And we have 1.5 microseconds latency. We have ASICs glued onto the sensors themselves to compress this data and send it out into this level 1 trigger. So here we're using deep neural networks for compression, variational autoencoders that learns to compress the data. It's exactly the same as PCA, basically. Find the directions of the data with maximum variance and store those. And then you try to reconstruct the data again from that embedded space, so you have the original data. So what do is, on ASICs in the detector, we put half of this model that encodes the data. Then we transmit the encoded data via high-speed optical cables to the level 1 cavern, where you either reconstruct it again, or you just operate directly on that embedded space, because it's probably more than enough. What's cool is that here we really have this extremely low power domain, so it's really relevant for wearables, edge devices. Every single weight and bias has been triplicated because we have a lot of bit flits. It's a lot of radiation, so similar to applications in space, for instance. And we can reprogram the weights, actually. So if we need a retraining, we can reprogram them, but the architecture must stay the same. We even have libraries to predict which parts of the networks is most sensitive to bit flips. Okay, in the level 1 trigger, we are doing a lot. I told you already we'll be doing 40 billion inferences per second. I give a few examples here. One thing we're doing is doing anomaly detection in the trigger. We learn the probability density of the data, and we try to trigger outliers in 50 nanoseconds. We do interaction networks in deep sets to identify what types of quarks were present in the collision, again, sub 160 nanoseconds. We can even do fully on-chip transformers in 90 nanoseconds. They're small, of course, for 500,000 flops, 9,000 parameters, but we can do them, and they perform well on low-level reconstruction tasks. We also work outside of physics for self-driving cars, seizure predicting brain implants, tiny ASICs that give a warning to the customer if a seizure is upcoming, and Earth monitoring and satellites. We have a lot in common there, compressing data before you actually send it to Earth. We also have a broad reach outside of physics. So our backend that we use to print silicon, Siemens actually developed that backend for us because they are also interested in using our library, because we really are one of the best in this low latency domain. I wanted to end with just a few outlooks. This is already challenging, but our field is now in a crazy phase of change. So this is the system we've talked about so far. This is the LHC, 27 kilometers. We are now planning the future circular collider. It's a 90-kilometer long ring where the idea is to go from the current energy we have and increase it by a factor of 10, so we can produce new heavy types of particles. This data transfer bottleneck will become crazy because we have better detectors and we will have now 1,000 simultaneous collisions. So inside the detector, it implies we will have to read out 250 terabytes per second for some of the subsystems. And we actually say we believe in 30 years that technology will be possible. Some parts of the detector will be at 1 petabytes per second inside the detector. So it needs to be received by ASICs and sent out. And that we are not very confident is actually going to work because we need all that cabling to power that readout. So we are looking at two solutions. The bandwidth is limited by the electrical and optical links. Either we do front-end reduction of the data on ASIC, or we have higher capacity transfers. So two of the blue sky things we're looking at for these two things is one, what's called eFPGAs. I don't know if you've heard about these. They're like FPGAs, but they're in ASIC design. So you have reconfigurable logic in ASICs, basically. So you can put machine learning at the source, fully reconfigurable logic on the detector front end, so you can really reduce the data transmission on this chip. And everything, the compilers and stuff is completely open source, so this is really, really cool for big scientific experiments. Secondly, we're looking at wireless, because if you can have cables, of course, wireless would be a fantastic solution. So here, we want to reduce the material budget by, instead of using cabling, using wireless. And the cool thing here is that we can really not increase the material, but increasing the transmission rate. And we can send a signal to several receivers, again, saving cabling. And we're also investigating using wireless for powering, basically, because that's also a big part of it. Okay, so that was it. If we're a big community working on all of these techniques, because it's not just CERN that has these big data problems. So we meet every month talking about new cool techniques, and we'll have a big conference at ETH Zurich on doing fast machine learning in the scientific domain. So thank you very much.